In steps 5 and 6, we're going to take the information that we calculated in the previous to get the member end displacement information that in this case was just only the rotation at B, that ek theta B was equal to minus WL squared over 144, and we'll back substitute those into the member end force displacement relationships. That'll give us values for the member end moments, which they'll then put down physically onto the member, from which then we can go and determine the shear moment diagrams and the qualitative deflected shape to finish off the initial part of this problem. So let's go ahead and get right into it here. We've got 4 ek theta B is equal to then a 4 times minus the WL squared over 144, and then we'll add to that the negative WL squared over 12, from which we will end up with the minus WL squared over 9. And then we come in here and put in the next one for MBA, we get similar looking results, but with the change in coefficient and the change in sign on the fixed end moment term, we get a different end moment, this one being positive at WL squared over 36. And then for MBC, we get 4 times the minus WL squared over 144, and there's no fixed end moment. That will be minus WL squared over 36. And then finally, when we look at this last one, it's going to be half of what we just calculated, so that'll be minus WL squared over 72. Now, one thing before we go charge off into a bunch of other work here is that we should do a real quick check, make sure that we have calculated things correctly, and it'll show up right here. Remember, MBA plus MBC was our equilibrium equation that we're using, and the sum of those is equal to 0, as it should. And that tells us that at least we've processed by hand this work correctly. We're going to take each of these and we're going to draw them the way they physically act down on the member. So over here at the far left, it's minus WL squared over 9, so it's going to act in the counterclockwise fashion. Note, this is the positive sign convention for slope deflection. We'll deal with the way we draw the shear moment diagram here in just a second. We get to the right end of that member and we have a positive WL squared over 36, or clockwise. And that means then when we go to calculate the end shears, of course we'll just sum moments at one end, and we'll find out that VAB is going to be 7/12 of the total load, and that VBA at the other end will be 5/12 WL. When we go to then reflect these onto the joint, then of course we flip them around, and the moment gets flipped around. It's the WL squared over 36. Come over here to the member BC, we have a negative WL squared over 36, so that's going to act counterclockwise on the member N. We get half of that also clockwise at the far end, and so we have a net counterclockwise rotation, from which then that means we have to have a force couple created by the shear going in the other direction and do the equilibrium there, and you'll get up and down WL over 24. Reflect this on over to the joint, and there's our moment. Again, we have equal opposite moments on the joint, but we don't have equilibrium in the vertical direction, which is going to come though from our B sub y, our middle support, which will be equal to 5 over 20, that's 10 over 24 plus the 1 over 24, so that's 11 WL over 24. We don't really need that to draw the shear moment diagram, but it is a helpful calibration of everything, because note what's going to happen here. Let's do it this way. We're going to go up to 7/12, come down to 5/12, and there's our beginning portion of our shear diagram. Notice that sort of tells us right off the bat that we're at 7/12 L here and 5/12 L here, telling us, of course, where the zero moment's going to be. And then we'll kick up to a net of positive WL over 24. It'll be flat, and we end up also at positive WL over 24 there. That's the moment diagram. And then the shear diagram. The moment diagram then is going to be starting off at minus WL squared over 9. It's going to end up over here at 1/4 of that. Right there. That's going to be second order curve. It's going to be reach a maximum right there. And then this one is going to go, we'll do the easy one first. 2-to-1 ratio here between those moments, minus WL squared over 36 to a now positive WL squared over 72. Well, that looks kind of bad. Right, so there we go. Now we got to go, of course, go find the maximum moment here. Now you go find this area under the shear diagram that tells us the delta will end up popping up, it turns out, to 17 WL squared over 288 for the positive maximum. And let's get our trusty French curve out to draw this in. There's our moment diagram. We can go figure out where the inflection points are at, roughly about in there or so. And of course this one's easy to figure out with the 2-to-1 ratio. It's at the 2/3, 1/3 location here. We've got a little smiley face for the deflected shape out here at the far right. And then we're going to have frowny face looking us all the way back. To the inflection point, and then we will go ahead and draw this portion in first. Let's not go down too far, make it too difficult to fit the rest of this in. And now we can finish this off. A little bit of break there. Should have a smooth transition right in that location. And there's our transverse deflected shape. And we got it.